All right, good morning, everyone. It's 9 a.m. I'll be your session chair for this morning. My name is Thomas White. I'm a staff scientist at the Scientific Computing Group in Photon Science here at DAISY. They'll be enforcing time limits with an iron fist, so watch out. Good. So the first talk is by a friend of mine, actually, Zdenek Matej from Max 4 in Lund. And he's going to be telling us about innovative data acquisition solutions with HSDS at Max 4. Once we've got the screen sharing. Yeah. Share the screen shortly. Yeah, that one.
Do you have a pointer? Oh, maybe not. This thing work. Okay, it's I would like to share what we do with HSDS. Good morning. I would like to share with you what we do with HSDS at Max 4 Synchrotron. Yeah, and I will mention that that's not my work, actually. It's based on work on very many other people, especially Felix, Jason, and Michele. Yeah, so what is Max 4 Synchrotron? Max 4 Synchrotron, like you are sitting in a synchrotron laboratory or like a larger laboratory. This DAISY has many accelerators. We are mainly synchrotron accelerator. This means that we are accelerating electrons and we are producing X-ray photons. Yeah, in 16 experimental stations, beamlines. We have 16 stations, and we are producing photons, we are converting to data, and this data are saved in HDF5 format with Nexus convention. Yeah, this is why I am here. And what was maybe, we are similar to DAISY Petra 3, you can visit them tomorrow. But maybe what we missed is that usually the light sources are having users. We are having about 1,600 users per year, yeah, and many of these users have never seen HDF5 file before, yeah. This slide should actually illustrate that data processing and visualization at light sources is a distributed problem, yeah, as detectors, data are coming from detectors and other sources, signal sources, but they have to be visualized and analyzed on laptops of our staff on site, right? On the laptops and desktop stations of users connected remotely from anywhere in the control rooms of our experimental stations, on our HPC, and nowadays also in a cloud environment, often maybe in future in open science cloud. Yeah, so it's distributed. Next slide is showing a timeline of important event of HDF5 of usage of HDF5 at Max 4 Synchrotron. It was mentioned, and it's on our, that HDF5 is here over 25 years, but earlier synchrotron light sources are here also about that time for sure. But we were using a lot other like proprietary data formats like TIFF. Yeah, I remember crystallography binary format, some type of raw formats. And but at some certain point, we started using HDF5 at Max Lab, the predecessor of Max 4. It was in 2014 when I came there. 2 years later, HDF group introduced H5PD and HSDS. And we have also inaugurated the new light source, Max 4, where we already used HDF5 routinely. I found what it is like. I found a slide showing that when there is even a sentence, but do not be afraid, you can always go back to spec. Yeah, so that was in 2016 where we were using it, and we were using PyMCA as HDF5 viewer. But later that year, because we recognized the need that we have to visualize not locally, but remotely, Jason Bruvik, who is now at European Spallation Source, started developing HDF5 Web GUI based on some development of HDF group. He just like continued that, and he developed something that was useful even like on the mobile devices. In 2018, we were aware of HSDS, and we started our own like internal project of investigating HSDS on Amazon Cloud. Yeah, this was again done by Jason, and but this was successful, but it was somehow difficult to get data into the cloud at that time. Yeah, so it was not much useful for us. In 2020, HDF Group introduced an HSDS POSIX storage. Yeah, and in the last European hack, it was in 2023. This means 2 years ago. Yeah, here at DESI, at the end of the hack, there was a tutorial about HSDS, where we could run HSDS on our laptops. And I came from that hack, and I said to my colleagues, "Yeah, people, I saw it. The HSDS is working nicely. It is very useful. Yeah, and I can run it with POSIX storage on my laptop. Yeah, we should try to use it even we don't have object storage. Yeah, and that helped us in 2024 to get HSDS into production at Max 4. So, I would like to speak about HSDS in relation to data acquisition and live data processing. At Synchrotron laboratories or light sources, data comes from different sources, from different type of detectors. That orange one in the middle is produced here at DESI. Yeah, and we are saving data from these detectors and other signal sources into files, usually HDF5 files, and these files we then give to users and they analyze them or visualize. There's a classical pipeline, like the creating of final data. For that, we are using virtual data sets to glue files together. We are using direct chunk write and read for getting performance, and we are using SWMR, single write to multiple readers for the user, for example, fast writing, and the user and other type of analysis reading. Yeah, like the classical workflow includes like writing and reading files a lot. Yeah, we write files from the detectors, and we read them into a processing pipeline, and then we produce again the result that we save as a file, and this file is then observed by the user and visualized. This we call ephemeral data. Yeah, it's quite. For that, we are of course using a lot shared network storage in order to exchange data between the places because the problem is distributed. So, it is very common. So first of all, I would like to speak only about data acquisition and live data processing. So I will remove the upper side, and then. And in this context, it is now popular to start using streams. Replace the first stage by using just data streams. So we inject data by data streams directly into the processing pipelines. Then we again produce some results and we visualize them. Yeah. So, and for that at Max 4, we are using a product developed or invented by Felix. That is called the DRANSPOS, a constraint map reduced live analysis pipeline for fast experimental feedback. Yeah. And the idea of DRANSPOS is that we have different detectors, different signal sources. They are usually hardware synchronized with triggers. And so the triggers are like forming events. This event data has to be merged, then processed, reduced. Yeah, and this reduced data, they can be visualized, for example. So this is how it usually works. In DRANSPOS, it is constrained, because you have to, at the beginning of the so-called scan, you have to load a map that we call the trigger map. There is a map where the signals will go. So for example, the start signal from all the data sources will go to all workers. Yeah, like virtual workers that are mapped to physical workers. So then you can, for example, prescribe that the first image from the first camera will go to a worker number 1, worker number 2, or to both of them. It may also happen that it will go nowhere, and it may happen that the given data source does not have a signal for that event. Yeah, so this is about DRANSPOS. This DRANSPOS allowed us to replace the intermediate HDF5 files by data streams, which are in our case mainly 0MQ streams, and we don't need the shared network storage for that anymore. It is the next step was when they were looking on this is that usually we again produce the HDF5 files in the reduction step at the end. Yeah. Or we connect some dedicated visualization to it. And the guys, Felix and Michele, they extended this idea by introducing HSDS. So we publish data into the HSDS, and on the data in HSDS, we are then connecting with the, I don't know, specific visualizers with H5 Web or with Silex Viewer. Yeah, and in this step, we have get rid of using the shared network storage also for the other ephemeral data, and we need only local storage now for POSIX backend of HSDS that we are using. So this is illustrated in this picture. We still have the ephemeral data here written to shared network storage, and by introducing HSDS, we will get rid of the shared network storage. We have now HSDS running on object storage, yeah, which is distributed storage, or on the local storage, just as a POSIX. Yes, so the shared network storage is gone from live data processing. That was the result, and I like that result. Using HSDS at Max 4 has synergies because we are quite modern in that fact that we have modern infrastructure, and like a lot of data acquisition is happening at Max 4 in data acquisition cluster that is based on Kubernetes. And in this Kubernetes, it is very easy to spawn an HSDS service for a given beamline. We are doing a very simple deployment. We created a custom image based on Conda. It is a single pod with having like a resource several cores. It is using the POSIX storage as a backend, and it is really unoptimized at all. Yeah. So, here is an example of an like a typical set of a simplified set of microservices for one of the applications, which is called streaming tomography. Streaming tomography is something like CT in the hospitals, where around you is rotating camera and X-ray source. Yeah, at the synchrotron sources, we cannot rotate the camera. We cannot rotate the X-ray source. So we are rotating the sample camera, and the X-ray source are static. So this means that in this type of experiment, we have camera images, but we have also motor positions. And when we glue them together and we do some computation, we can reconstruct the volumes. And visualizing them in streaming tomography, we are not reconstructing the full volume. We are reconstructing only 3 orthogonal slices that can be anywhere in the volume. And everything is running live. And this is a typical example. Camera data go to detector control unit, that they go to the frame receiver. Frame receiver has the property to generate HDF5 image file. Whereas the motor encoders data, this is the other channel, go to another receiver. Receiver is communicating with control system. Control system can create another HDF5 file that contains motor positions. This is glued by HSDS into the HDF5 file with the exchange convention for tomography, and that's the final data. But that's the side channel. This is not important for live data analysis. In live data analysis, the data from the receivers continue to in Kubernetes. You have into the dtranspose ingesters for the different signals, and they are distributed to workers. Workers are republishing data for another microservice that is called streaming tomography. Streaming tomography is doing reconstruction on GPU, and publishing results with its specific REST full API, or pushing the results into HSDS. And to HSDS, I can connect with Jupyter Notebook, I can connect with visualization clients, and so on. So, when the users consider data in HSDS as like useful, they can pull out the classical HDF5 file by hsget command if they want. This is like a visualization connected to HSDS. So the data are stored in HSDS. I can, like the Kubernetes are generating for me this nice like endpoint, then max HSDS dot DAQ, max IV.LUC, and then there is a path of the file in the object storage. I can use standard Silex viewer to connect to this data. I can use H5ID in the Jupyter notebooks. I really like that solution. So that's about it. That was a typical application. And now, that's the last slides that I have here. So if you think about this scheme, we still have here this local POSIX storage that we are using. Yeah. So when we generate some result by data reduction, we push it into the HSDS, it will save it into the POSIX storage. Then we want to access to it. It will read it from the POSIX storage and give it to us. So that's nice, that's good, but it's an overkill. We don't need that. Yeah. My colleagues, they did, for simplifying things, they did even one more step forward. They have get rid of that POSIX storage each, and they're exposing the results in memory, which HSDS API. Yeah, so all files are gone. Yeah, we don't have them at all. Yeah. But we have the HDF5 data model, and that I like. So, this is the last slide, how it is done. So dtranspose, we don't have a special project doing that, but dtranspose has inside utilities in helpers that are called H5 dictionary, and that contains router. So when you want to do this, expose data, you don't need the transpose. I just took this component of it. I will just import this router from dtranspose. I will create a fast API application. Yeah, then I will add a router that I just imported to that fast API application with a prefix result. Then I create a function. The only this function is returning a dictionary. Yeah, and dictionary is representing my HDF5 data. Then I assign this function to the gate data function of the application, and I start the application. And the thing is, and now I am running in a publisher. For example, in IPython notebook, if I could show a demo, if it would be possible. And in one notebook, I am running this publisher. And in other notebook, I just use H5PD to access this data, this service on the port 8000 with the prefix results. And I can export this data with H5PD. Yeah, that's all. So in this demo, I would take a current time, yeah, and publish the current time. Yeah, and the other notebook could just access this time value, the current time, and print it. So it's it's really live. Every time you execute this function, it will give you an accurate time from the other notebook. Yeah, and it is using H5 the HDF5 model to transfer data between these two entities, or to publish data. Yeah. So in summary, at Max 4, our recent trends in data acquisition with HSDS, so HDF5 at Max 4 is that we are trying to utilize HSDS instead of using shared network storage, yeah, which was enabled by introducing POSIX storage backend, because we still do not have the object storage, but this allows us to work with that. And we are leveraging tools like Silex and H5 Web and H5PD to access as data from our experimental pipelines. We have a finite number of engineers who are developing data processing pipelines at Max 4. And it would be, of course, nice to do a specific visualization for each of the applications. But by leveraging the HSDS as API and the tools, we can do different pipelines that are storing different results with HDF5 data model, and we can access these things with the generic tools. Yeah, and we found storing data all the time as an overkill for our data acquisition applications. So we implemented very primitive, read-only H5PD access to the data in the memory from our data reduction pipelines. Yeah, so we don't have files, but we still have HDF5 data model. I would like to thank you for your attention, and also thank to my colleagues, especially Felix Engelmann, for being very enthusiastic about this thing and coming with so many ideas as how to do this. Is Michel he's now at Ohio. Michel is continuing work on DRANSPOS and many of the data analysis pipelines. Jason Brunvik helped us was exploring the initial HSDS possibilities is at Max 4, and now he's at the European Inspiration Source. And then the things go so well at our facility because we have good IT infrastructure, this Kubernetes cluster. For that, we are grateful to Andriy and Dmitry, and we are grateful to HDF5 group and the whole community for developing such nice tools that we can use. Thanks.
Okay, thanks. Very nice talk. What kind of frame rate can you get when you do, for example, the tomography example?
So the tomography itself is able to, the streaming tomography can run on the speed of the camera. These free orthogonal images can be updated with minimum latencies is with every frame that comes. And the cameras that we are using are like industrial, good high-speed cameras, but only like 120 hertz. Yeah, but that would be too much. Like if we would be updating the images on the visualization, like 120 times per second, that we would completely overkill the computer. Yeah, and the images are large. They were like 4,000 by 4,000. Yeah, so resolution is giant, and this means that honestly it is running on 1 hertz because that's the capability of a computer with 1 gigabit connection. Yeah, to get data without compression and with optimization.
You run into network limits.
Yeah. It's like we would need stronger connections from our backend to the front end, and or using things like Caterva2 that allow us to compress between the backend and front end. Yeah, that would help us, like with such images.
Very nice. Any other questions or comments? Yep.
Yeah, morning. Thank you very much. And I have a question about that Silks application. So when you pointed to like a HTTP endpoint, basically, that means that your client and the H5 file are actually on a different hosts, right? So does it imply that you actually transfer the whole file to the client, or how does it work?
So I think that it is like so the application that I was showing, it's HSDS as
No, Silks. I mean, on one of your slides you had like Silks, View, and then HTTP, whatever. .h5.
Yes. So where I was connecting, this is the endpoint. And Silex wants like a connection to the file because it is using as a like a root entry as a top entry from where it starts, when it starts like exploring the initial data set. This is quite interesting where the HDF5 model starts. I don't know, like if it starts on this root entry level or on the level of files. I think not. Yeah, it starts there. So this is why this is the beginning. And because it's using HSDS, it is really transferring only this part of data that are accessed, or only for what I ask. Yeah, it's like the API is happening on HSDS backend. Yeah. Then I have to say I don't know exactly the details of or the implementation of my colleagues. It's quite visible that in our primitive implementation of this HSDS like H5Py dictionary, it is not HSDS. Yeah, we have no chunking and such things. This is missing in our model. So we are really transferring, for example, the whole image. Yeah, we cannot transfer only piece of it. I think maybe piece of it, yes. Yeah, I do not know what is the capabilities of HSDS updates simply. So that's only the piece of data that should be transferred is transferred, but it's transferred uncompressed, if I am right. Yeah.
Thanks so much. Thank you.
Yeah, I'm Thomas Vincent for ESRF. I maintain Silex, and to access HSDS, it's using H5PyD. It's a hidden feature, let's say, but if the file is on disk, you will use H5Py, but you can access HSDS if you pass a URL because it's using H5PyD Python package to access the REST API.
Okay, there's a couple more questions online. Andy Gotts is asking, are you able to have concurrent access to files while they are being written?
Concurrent access to files when they are written. We are not writing any files.
At all, even
At all,
at the
yeah.
end,
In the data acquisition that I have shown, we are not writing a single file, so we don't but okay, we provide concurrent access to all the data sets that wants to be anybody wants to access, not the files, but the data in the memory or in the cloud, let's say, like HSDS and how it's called, and our H55 dictionary helper in dtranspose is allowing concurrent access.
And there's one more question online from Sonal Patel. If you could unmute yourself.
Hello. Yes. In your previous, in beginning of your slides, you mentioned about Nexus. So I just wanted to ask, like, where does the Nexus come in the acquisition workflow? I mean, it's directly acquired in the Nexus standard, or you like convert in between after the acquisition?
Okay. I was putting a Nexus who's like we are using HDF5, and in HDF5 with data, HDF5 model allows us to have Nexus file format decorated our data with Nexus file format. And that we can do at any moment. We are using HDF5 data model. Yeah, so this means in both in HSDS, because HSDS allows you to have attributes. So you can have Nexus attributes, and this means Nexus model. You can also also our, as I demonstrated, our H55. I maybe didn't mention that explicitly, but it was visible in the code. The H55 dictionary allows us to have Nexus attributes also for the dtranspose helper. So even the dtranspose is capable of publishing data with the Nexus convention on the top of HDF5 data model. Yeah, so we have data, we can decorate the data with Nexus, which is just a synergy with tools like Sylix, because Sylix understands Nexus, so it can automatically visualize the correct data set in the file that we are publishing to it. Yeah.
Thanks.
Thank you.
And there was one last question, I think, from Thomas Vincent online. Or was that a hangover from your comment before? I don't know, it says joining, so maybe we'll leave that one for later and move on. So thanks very much, Zdenek.
Thank you.